Hi everyone, this video is going to walk you through 5 worked examples of how to utilize u-substitution for evaluating integrals. The key is to determine correctly what to allow u to equal. And sometimes you have to think ahead with these. You have to determine what you're going to allow u to equal, knowing that your next step is going to be finding du, which should yield a derivative that should allow you to replace something in the integrand. If you take a look at this first example, we have the antiderivative of the quantity e to the x plus 1 times the quantity e to the x plus x. So if you think about what you want to allow u to equal, and knowing you're going to take the derivative next, it might make sense to allow u to equal e to the x plus x. The reason is when you go now to take du, you're going to get e to the x plus 1, which notice you can eliminate right there. And of course that's multiplied by dx, your differential. Your next step would then be to rewrite the original problem in terms now of u. Rewriting it then, we simply have, in place of e to the x plus x, that's your u, the e to the x plus 1 quantity times dx, that's your du, as you can see by how we started working it out on the side. So all we're really doing is the antiderivative of u du. As we take that, of course, that's going to be 1/2 u squared plus c. We substitute the quantity that we allowed u to equal back into the equation, and we obtain that for our final answer. Remember that you can always check these by taking the derivative of your answer. So let's try it with this one just as an example. If we take the derivative, that's going to involve the chain rule. So we'd have 1/2 times 2, so that's 1. So we'd have like 1 and then times e to the x plus x, and that's going to be raised to the first power. But now according to the chain rule, we need to go inside, multiply by the derivative of e to the x plus x, and that yields e to the x plus 1, which you can see matches the integrand we started with. The constant c, of course, that derivative would be 0 because it is a constant value. Let's take a look at another one. There definitely are some tricks as to what to allow u to equal. Typically it is going to be an inside quantity, and remember that when you take the derivative of what you allow u to equal, you want to be able to eliminate something else in the integrand. So on this one, if we allow u to equal that quantity in the denominator, the 1 minus 2x squared, notice when we take the derivative of that, we get negative 4x dx, which is this part right here. So that whole part right there, we're going to be able to replace with du. As we rewrite this then, remember this whole part becomes du, 1 minus 2x squared, that's our u. Now we're going to bring that up to the numerator because it's going to be much easier to take the antiderivative then. And all we're doing is the antiderivative of u to the negative second du. When we take our antiderivative of that, we get negative 1 u to the negative 1 plus c. We substitute u back into our expression, and you can rewrite this if you want. You could drop that u to the negative 1 to the denominator if you wish, and you end up with negative 1 over 1 minus 2x squared plus c. Again, you could take the derivative of this and you'll notice you get this original integrand back again. I very much encourage you to do that on the first ones of these you're trying. It's a great way to verify that you are doing these correctly. Let's try another. On these trig problems, remember that if we have cosine squared of x, for instance, what that really means is cosine of x, the quantity squared. I recommend rewriting it that way as you start these out and learning how to do them, because sometimes it helps you determine a little bit more easily what u should equal. In this case, we're going to allow u to equal that cosine quantity that was squared, and just the cosine part, because when we take derivative of cosine, that's going to be negative sine of x dx. Remember, you're doing derivatives there. A lot of people mess up their positives and negatives on that because they're thinking they're doing antiderivatives as opposed to regular derivatives. Now notice here's the sine of x dx right here that you can eliminate, but we do need to divide over that -1. So we would have a -1 du is going to be replacing that sine of x dx. Our next step then is that we want to rewrite this. We can bring that -1 to the very front, because -1 du is going to be replacing the sine of x dx part. So the -1 we could just bring to the front. Remember, cosine of x was your u, so we have u squared there, du, and that's all you're taking the antiderivative of. Notice as you're doing these, one of the main purposes behind u-substitution is to take a somewhat complicated problem and turn it into a very simple antiderivative to find. If you look at these that we've done so far, they're very, very simple antiderivatives to do in the end. We're going to leave the -1, taking the antiderivative of u squared. Of course, that's going to be 1/3 u cubed plus c. We substitute the u back in, so we have a -1/3 cosine of x cubed plus c. Of course, you can rewrite that instead as cosine cubed of x. Either notation is fine. It does not matter at all. Once again, you can take the derivative of this. That's going to involve use of the chain rule, and you'll notice you get this original integrand back again. When you use u-substitution with integrands that involve exponents, typically you're going to allow your u to be that was in the exponent. Now, a little trick with this one is that in order to properly identify what u needs to be on this, you do have to rewrite this problem first. The square root, of course, is a 1/2 exponent, so we're going to rewrite this before we even decide what u is going to be as 10 raised to the 3x over 2. The denominator in the 2, that's really the square root. Because once you rewrite it that way, it becomes a little bit more apparent as to what your u should equal. We will allow it to equal the exponent 3x over 2. Taking du then, we get 3/2 dx. Well, there's the dx that we want to eliminate. We're going to have to divide over the 3/2, so of course that means multiplying both sides by 2/3. So in place of dx, we're going to have 2/3 du. So let's rewrite what we have. The 2/3 can come to the front. So we have 2/3 antiderivative of 10 to the u, because remember this was our u right here, du. So the 2/3 du together replace the dx. So we'll leave the 2/3. This is where you need to recall your antiderivative rule for exponential expressions. So antiderivative of 10 to the u is going to be 10 to the u over natural log of 10. Now we simply substitute our u back in, and the 2 over 3 natural log of 10, together that basically acts as a coefficient, and that would be our final answer. Please note it would be very, very wrong to multiply that 2 and the 10. Order of operations, you cannot do that. So we have one more example to look at. Here we have another exponential expression of which we are taking the antiderivative. Once again, we're going to allow our u to be the exponent square root of x. And of course, that's x to the 1/2. Taking the derivative, we have 1/2 x to the -1/2 dx. Now, notice what happens if you rewrite this a little bit. We're going to want to multiply both sides by 2, divide over the 1/2. So we have 2 du, but if we rewrite this x to the -1/2, notice how that's 1 over square root of x. And here's all the stuff that you can replace with that 2 du. Again, the whole purpose behind u-substitution is to take an integrand, which is somewhat complicated, very much simplifying it by putting it in terms of another variable, in this case, u. So that square root of x and the dx all get replaced by 2 du. So the 2 we can put in the front. And now we're simply doing antiderivative of e to the u du. And of course, we all know how simple that is. Antiderivative is going to be e to the u. And our final answer is 2 e to the square root of x plus c. Once again, I encourage you to check your answers as you're just starting to learn this by taking the derivative of the answer you obtain to make sure you get that original integrand back again. It's a great way to verify that you understand this and that you're doing it correctly.